All right, the second important point from this chapter is that the kinetics of non-cooperative enzymes, and I alluded to cooperativity before when we discussed the structure of hemoglobin, that binding of one molecule can affect the binding of further molecules. But in the case of simple enzymes, when they only have one binding site, they do not have this cooperative property. So these simpler enzymes can be explained by the Michaelis-Menten model, which yields a mathematical formula for the reaction rate. Okay, the Michaelis-Menten scheme, a reaction scheme, is the following. You have the enzyme plus the substrate can react to form a complex of the enzyme and substrate, and that can further react to form the dissociated enzyme and product. Let me label these two reaction arrows, rates K1 and K-1. K1 here is a second order rate constant, which depends on the concentration, so the total rate depends on the concentration of the enzyme and the substrate. K-1 is a first order rate constant, which only depends on the concentration of the ES complex. Now this reaction, this first reaction here, is not a covalent reaction, okay? So the enzyme and the substrate react non-covalently. So this complex, of course, is a non-covalent complex, an association. So it's not a chemical reaction in the sense of a covalent bond forming or not forming. The second reaction does involve chemical reactions in the conventional, in the sense of covalent bond forming and breaking, because the substrate is going to convert to product. Now, one of the assumptions of this model is that the product itself does not remain bound to the enzyme for any appreciable amount of time. So essentially, you go directly from the complex, which is called the Michaelis-Menten complex, or the Michaelis complex, to the dissociated enzyme, which is ready to go and catalyze more reactions over here, and the product, which floats off there. And we're going to label that reaction rate constant K2. Okay, and note that that is a first order rate constant too, so it has units of per second or inverse second. This has the K-1 constant also has units of inverse second, but this being a second order rate constant is per molar per second. I also want to point out one thing. I went to some length to explain that enzymes change the reaction rates, but they don't change the equilibrium between the substrate and the product, right? That equilibrium requires a backwards reaction from the product towards the enzyme. But you'll note that I haven't put that arrow there, and this is very common. We leave that arrow out. The reason we can do that is because typically in biochemical context, so in the cell or in an assay in the test tube in the lab, the enzyme reactions are run in a non-equilibrium state. So the initial state of the reaction has a very small amount of, has no product, for example, if we're running an assay in the lab. So that product does not, because it's such a small concentration, there is no appreciable back reaction, so it can be ignored. In the cell, often the product is another metabolite or molecule that is processed in further metabolic reactions, or maybe it's secreted or something, or it goes off, so we don't have to worry about the back reaction there either. Okay, to analyze this mathematically, we're going to make an assumption. The assumption is going to be, the number one assumption is the steady state assumption. Okay, so that's one assumption. The steady state assumption will tell us that the rates of the reactions are such that the concentration of, for example, the the Michaelis complex here does not change in time. Now that could occur in the test tube if we're doing an assay in an experimental assay of the enzyme, because we set up the situation with no product initially. We mix enzyme and substrate. They quickly come to some sort of maybe equilibrium, and they reach a steady state where you have a constant concentration of this complex. In the cell, you might have constant conditions producing product at a constant rate, and this might be a good approximation for that. So let's write out the mathematical statement of that. So if you consider the rate of formation and dissociation of the Michaelis complex, so that's K minus 1 times the concentration of the complex plus K2 times the concentration of the complex. That's the dissociation rate, and the association rate, of course, because there's only, if you look back at this scheme, this reaction scheme, there's two arrows coming out of ES. One's got a K minus 1, one's got a K2 on it. That takes care of these two. And then there's only one arrow coming in. That's this association here. So that guy is just K1 times ES. So this is, if you will, the first mathematical equation that comes out of this model. Now I'm going to define something called the Michaelis-Menten or the Michaelis constant, which is Km, and it looks a little like an association constant or a dissociation constant. And I'm going to define it this way. The way you would define a normal dissociation constant or an equilibrium constant that would give you the ratio of the products of these concentrations to the concentration of the complex. You can show very simply from this equation right here that that has to be equal to K minus 1 plus K2 over K1. And you can understand this equation simply by realizing this sum right here, this is the sum of the rates for the dissociation or the leaving the complex. The complex can lose moles by either going this way or that way, and the sum of those two rates is represented here. The only way the moles of the complex can increase is by this reaction coming forward, and that's in the denominator. Okay, so this is an important constant that plays a role, as you'll see later. Okay, so now we need another equation here. I'm going to move this up here. I'm going to leave those equations right there. And I'm going to add another an equation which is very useful for putting this in a formula in a way that can be applied to enzyme assays that we would do in the laboratory. And this is basically conservation of matter, or conservation of enzyme, I'll call it. Because if you think about it in an actual reaction, you would, you'd add the substrate and the enzyme into the test tube, and you know exactly how much enzyme you would put in. That enzyme would be conserved. It might be in form of a complex, but or a free enzyme, but the sum of the enzyme, the free enzyme, and the complex would always equal a constant. So that is the total amount of enzyme that you put in originally. If you think about this equation, must hold true. This is the concentration of enzyme in the original assay that you throw into your test tube, into your volume. It may start reacting and form complex, but the free enzyme is left, but the sum of those two will always equal the original one. Okay, before I go on, I want to make a few definitions. Whoops. Okay, definitions. Now let's think about what we're trying to derive here in using this model. one of the things we're interested in is the total rate of the reaction, or actually the velocity of the reaction. Now the velocity of the reaction, if you look back at this reaction scheme, let me drag it back here for a second. This reaction scheme, the only place that the product comes from is this reaction here, and its rate will be K2 times the concentration of ES. That will be the rate of product formation. So that's what we're interested in. How fast is the product formed, right? So the reaction velocity here will be the rate of product formation, which will just be K2 times that concentration of that complex. Now, the maximum velocity we call Vmax. If you think about it, that would be if the concentration of the enzyme complex here was equal to the total, right? So the maximum this can be, the maximum the complex concentration can have, is the total concentration. So this is the Vmax, we call it, the maximum possible velocity in the reaction when the enzyme is, as we say, saturated. So we call this saturation of our enzyme, or saturating conditions of the assay. Now to solve for the Michaelis-Menten rate equation, what I'm going to do is I'm going to take this equation right here, which is essentially equivalent to the steady state approximation, and I'm going to plug in for E what I have from equation 2 here. So the concentration of enzyme at any point in time will be the total minus the amount of complex. That will give me an equation which only contains the complex and the substrate, and also the constant Km. So let's write that right here. So we have Km equals E total minus ES, and that's times the substrate concentration divided by the concentration of the complex. Now let's do a little algebra here. We get E T times S over ES. And over here you'll notice that the ES is cancelled in the second term here. So there we just get minus S. Alright, you will see where I'm going in a second here. Let me move this up. So that's our current equation, our current state of affairs. Now I'm going to rearrange and solve for ES. So we can bring this substrate concentration over to the other side, and then I'm going to flip the order. So let's put E T times ES on this side, and that will equal Km plus the substrate concentration. And then what I have left over is this ES on the denominator here. Okay. Now what I'm going to do is I'm going to solve for this concentration, because if you remember, let me go back here and show something. The velocity of the reaction is proportional to the concentration of the ES complex. So if I can solve for that, all I have to do is multiply by K2 and I get the velocity of the reaction. That's the strategy. So let's go back here. Remember, here's where we are in the equation. Let's solve this now for ES. All I have to do is flip this over and multiply by ET and times S. In the denominator, I get Km plus S. Okay. Now this is looking good because when I multiply by K2, I'm going to do a little magic here. I'm going to multiply this both sides by K2. I notice something. What I get is the velocity of the reaction here, which is what I want. So I'm going to replace that with the velocity. So that's equivalent. This V is equivalent to this, right? But over here I notice I get something which I defined previously. Remember, this is the maximum amount of the complex. Let me move back here and show you that. Here we go, Vmax, right here. Right? Because the maximum amount of complex is this ET. So K2, I'm going to replace this with that Vmax, which is a common way to write this. So you get Vmax times S over Km plus S. And this is the classic Michaelis-Menten velocity, reaction velocity. Let me graph this a little bit. Let's look at some of the properties of this equation. Let me draw a little plot of this. I have substrate on the horizontal axis and reaction velocity on the vertical. Okay. All right, at small substrate concentration, so this is down here on the axis near 0, you can see that this number will be much smaller than Km, whatever Km is, so we ignore that, and we see that the answer will the velocity will be essentially proportional to the substrate concentration. So it's going to start off linear. But as it gets larger, let's see what happens. As it gets larger, eventually this will be much larger than the Km value. In which case we can ignore this, and it's going to be essentially equal to the substrate concentration in the denominator, which will cancel in the numerator. And what we'll find is that it will be proportional or equal to Vmax. So it'll go up like this, and then it'll roll over, and it will approach an asymptote here. And the value of that, of course, is Vmax. Also, let's look at what happens when the substrate concentration is equal to Km. Then what you get in the denominator is 2 Km, and this will be Km. And this will cancel. This factor of Km will cancel the 2 Km, and you'll get Vmax over 1/2. So that's about right here, 50% level, which is right there. So this occurs when the substrate concentration equals Km. So let me put this as Vmax over 2. Also, this functional form here, this functional form is known as a hyperbola, and this is often referred to as hyperbolic kinetics. It is also the same. You think about it, it's the same as the binding curve. Now, the binding curve. What's the binding curve? Let's go back a second. The binding. If you look at this, let's go all the way back to this reaction. Okay. Here's the reaction. Now, if you forget about the formation of product, if you just think about this complex right here, imagine that you're trying to derive the amount of complex as a function of substrate. So you're adding substrate, and you're just forming this complex in equilibrium with the dissociated state. And assume that that has an equilibrium constant. Here's where we get with the meaning, where we interpret this Km a little bit. Imagine this Km is the equilibrium constant describing the equilibrium between these two. Okay? With that in mind, let's zoom all the way down. Go back to my beautiful graph. What you would get in that case is a curve just like this. So remember that this velocity is proportional to the concentration of the complex. So what you would see is that the concentration of the complex would increase in a hyperbolic manner, and when the substrate is equal to the equilibrium concentration, the substrate concentration, you would get half of your enzyme bound to substrate. I also want to add a comment about Vmax here. Km, as I said, can be interpreted as when your enzyme is half saturated with substrate. But Vmax, when you reach Vmax, that is obviously when the enzyme is entirely saturated. So that is what we call saturation conditions, when the enzyme is 100% of the enzyme is bound by substrate. Now, in those conditions, the limiting rate, or the limiting factor in the rate, is how fast the enzyme can catalyze the reaction, and the substrate concentration is so high that as soon as the substrate is turned into product, right, as soon as that substrate converts the product and is released, there's so much substrate around that that active site is immediately occupied by another substrate molecule. So the time for the substrate to find and get in there and bind to that active site is insignificant. The limiting rate then is just how long that reaction takes once the substrate is bound. That limiting rate is called the kcat, or the catalytic rate, the intrinsic catalytic rate of the enzyme. And it's often called the turnover number. And you can see that kcat in this case is just going to be the Vmax divided by the total enzyme concentration. Why is that? Remember that the rate at saturation conditions, right, the rate is Vmax. So that's up here. Now that has units of molar per second. Kcat is just a first order rate constant. All right? It only depends on the concentration of enzyme. So the Vmax should equal the kcat times the total enzyme concentration, because all of the enzymes are occupied by substrate. Now I'm going to go back to the original model here and point out, in the case of this simplistic model, the kcat is equal to K2. All right? So for this Michaelis-Menten model, K2 is equal to the kcat, and sure enough, it does have units of inverse second. Lineweaver-Burke plots really were more useful before the age of computers, when nonlinear fitting became possible. A Lineweaver-Burke plot is an alternate way to plot the velocity in substrate versus substrate concentration. It involves a transformation of variables, and it's an inversion or reciprocal transformation where you plot the inverse of the velocity here versus on the horizontal axis you plot the inverse of the substrate. Now up here I've written out the Michaelis-Menten velocity function that we derived earlier. Below, I've transformed that by inverting. So I've just taken the reciprocal of the velocity and the reciprocal of the right-hand side. And when you do that, you can show in a few simple steps of algebra that you get this equation. And note that this shows that if I think of this as one variable, this variable is proportional to this variable times a constant plus a constant. And you'll recognize this as the formula for a straight line, where this is the y-intercept and this is the slope. Here I have a graph of the reaction velocity, just like I plotted before, starting out at 0, a hyperbolic curve that goes up to a maximum reaction velocity, and at a value of the substrate concentration equal to Km, you get Vmax over 2. Below that I have the same reaction velocity but plotted using the reciprocal variables. So 1 over the velocity and 1 over the substrate concentration. Now let's think about what this does. When the substrate concentration gets very large, so out here, it's equal to Vmax. Now when the substrate goes to infinity, what happens is the reciprocal gets smaller and smaller and smaller. In fact, it goes to 0. So that means at 0 on this curve, at 0 on the horizontal axis, it should have a value of 1 over Vmax, because we're plotting 1 over the velocity here. We know from before that this curve, when it's the inverse of this curve, should have a constant slope. We showed that mathematically before, and here I've indicated what that slope is. If you also look at the form, if you trace this slope backwards, you'll realize that it has to intersect the horizontal axis at a value of minus, there's a minus sign missing there, minus the inverse of Km. You can see that simply by the fact that the slope is Km over Vmax. Think about it. Here's this triangle. We can use this triangle to calculate the rise over the run. The rise will be 1 over Vmax. So there's the 1 over Vmax right here. And the run is the inverse of Km. So we divide by the inverse of Km and we get a Km in the numerator. Okay, let's test your understanding. Here is a Langmuir-Burke double reciprocal plot of a reaction velocity, inverse reaction velocity, against an inverse substrate. From this graph, you can determine both the Km and the maximum velocity. So that's what I want you to determine now. See if you can estimate the Km, the Michaelis constant, and the maximum reaction velocity, Vmax, from the data in this graph. Okay, let me show you what the solution is now. We can, first of all, easily get the Vmax just from the y-intercept here. This y-intercept appears to be around 1500. So that means Vmax inverse is about 1500 inverse molar seconds. If we invert that, we get 6.7 times 10 to the minus 4 molar per second, which is the final answer there, okay? That's for the Vmax. Now, for the Km value, well, we can get the slope, the Km from the slope. Remembering that the Km over the Vmax is the slope, we can merely estimate the slope and multiply that by the Vmax that we just got. So what's the slope here? Let's look here. The slope, let's estimate that. I noticed that at 50 inverse molar, the inverse is about 4,000. And at 0 we see it's 1500. So the rise here would be 4,000 minus 1500. And the run is going to be 50. And the units here, if you think about it, they're going to be inverse molar second divided by inverse molar, which just leaves you seconds there. And we're going to multiply that by Vmax, which we just figured out is, I'll go up to a couple of 3 sigma figures here, 10 to the minus 4 molar per second, which equals 0.033 molar, which is 33 millimolar. The Michaelis-Menten model can be modified to include the effects of inhibition. So this is inhibition from other molecules which might mimic or look like the substrate, or might mimic the transition state of the of the Michaelis-Menten reaction. And this is a very important topic because biological regulation often involves inhibition. You might have a product of a long line of metabolic steps might inhibit the early steps in the reaction, the early steps in that pathway, because you don't want to waste important biological resources, molecular resources, when you've already got lots of product at the end. You need to inhibit that pathway so you don't waste a lot of the resources of the cell. In addition, drugs often work by inhibiting molecular targets, which are often proteins or enzymes. I'll talk about 4 modes of non-covalent or reversible inhibition. The first is competitive. Now, this mode of inhibition is very much like the original model. We have the Michaelis-Menten reaction, but in addition, in parallel to that, we have a reversible inhibitor which can form a complex, a non-covalent complex with the enzyme. And this typically is a molecule which binds in the same binding site as the substrate. And because it occupies that binding site, the substrate cannot bind. This second reaction here, this one right here, has an equilibrium constant associated with it, which is called the Ki. So in equilibrium, the enzyme will exist in equilibrium with a non-productive inhibited complex. All right, let's think conceptually about this model, what it implies, without solving the detailed mathematical equations. Let's think about what this could mean for the equation, for the system. Because the enzyme, the inhibitor occupies the same site, if we increase the concentration of substrate, it'll tend to occupy the site much more frequently and prevent the inhibitor from binding. And that implies that as we increase substrate concentration, eventually we can outcompete the inhibitor. And we can bind almost all of the enzyme with the substrate, so that the maximum velocity in this case, in the presence of inhibitor, the maximum velocity will still equal the maximum velocity in the absence of inhibitor. But you might expect that, let's say, to get to 50% occupation or 50% saturation, normally that requires the substrate concentration to equal to Km. In this case, the substrate concentration has got to be larger than the Km, so you expect the Km to increase. Now graphically, let's represent this change. What I'm going to do is I'm going to draw a Lineweaver-Burke plot where we have the inverse substrate and the inverse velocity. We expect both of these to intersect at the same y-intercept, Vmax inverse. Let me draw the uninhibited reaction right here. Now remember that uninhibited reaction has a slope which is Km over V, which is Km over Vmax. Now as you add inhibitor, remember to get to 50% maximum velocity, now the apparent Km will be larger. You have to go to a larger concentration of substrate in order to get 50% saturation, right? But the slope of this line is proportional to Km. So if Km gets larger, but remember Vmax is the same, that intercept is the same, then this slope will get larger. So this is the inhibited curve. The inhibited curve has a steeper slope, but the same intercept here. And if you look at the extension to negative inverse substrate, which is non-physical but has a mathematical interpretation, you see it shifts towards the origin because Km, excuse me, gets larger, so the inverse of Km gets smaller. Now I won't derive it, but the apparent Km in the presence of inhibitor takes on this value. So I'll write Km prime for what the apparent Km is, and it's equal to the original Km times a factor which is larger than 1. Okay, that's the factor. And you can see that this factor here is larger than 1, so the apparent Km increases. The next form of inhibition is pure non-competitive. In this mode of inhibition, the enzyme can bind the substrate and react to form enzyme plus product, but in addition it can form a complex with the inhibitor. Now what is non-competitive is that the inhibitor will bind to a different site than the substrate on the enzyme. So it doesn't block the binding of the substrate, and in fact you can have inhibitor and substrate both bound at the same time. In this form of inhibition, note that the inhibitor can still bind to the complex even if it's bound to the substrate. So that means even under saturating conditions, when the enzyme is completely bound to substrate, the inhibitor still binds and can take some of that complex, active complex, out of commission into this inactive form. That means it reduces the Vmax. So we expect Vmax to go down as the concentration of inhibitor increases, okay? In the pure form, the binding or the association constant of Km is not affected. So in other words, the substrate can bind to the EI form, going from EI to ESI, just as easily as from E to ES, so that the Km does not change. Okay, now what effect does that have graphically on the Lineweaver-Burke plot? Let's use what we just learned, or the assumptions we just made about the properties there. We noticed that the Km does not change. Remember, the inverse of Km graphically, if we go into the negative, which is the unphysical but useful portion of the plot here, the negative inverse substrate value, we find that the x-intercept will not change. However, both the slope and the y-intercept will change because the Vmax changes, and the Vmax is the intercept, so that will change, and that necessarily implies that the slope will change. Now let's think in what direction. So how this changes as we increase inhibitor concentration. We expect Vmax, as we said before, Vmax to go down as the inhibitor concentration goes up. So the inverse will increase. So if you think about it, this is the direction of increasing inhibitor concentration. So as you increase the inhibitor concentration, you get a steeper slope, but the x-intercept remains constant. Now, nothing is quite as simple as the simplest models, and Km is usually affected, okay, by the binding of the inhibitor. What does that mean? Let's go back to the reaction mechanism. It's the same scheme, reaction scheme here, okay? But what we find is that the Km, the binding of the substrate to the EI complex, is different than the binding of the substrate just to the enzyme alone. That turns out to affect the Km value. That affects the equilibrium constant for the binding of the substrate, or affects the apparent Km value. So now at constant inhibitor concentration, we will find that the slope will vary, as we saw before, but now the x-intercept will also vary. Let me draw that for you. So we have our double reciprocal plot, and then there's our negative part of the x-axis. And what we find is that, yes, the slope gets steeper, but in addition, the x-intercept moves towards the origin. The apparent Km value gets larger, therefore the inverse gets smaller. This is increasing enzyme inhibitor concentration. The last form of inhibition that we'll look at is uncompetitive inhibition. In this reaction scheme, you get the formation of the productive Michaelis complex, which can react to form the dissociated enzyme end product. But that substrate complex can react with the inhibitor, which can only bind in the presence of the substrate. So this forms a non-productive ternary complex, which involves the enzyme bound to substrate and the inhibitor. The inhibitor does not bind to the free enzyme. It needs the substrate. So for example, this could be binding involves some interactions both with the substrate. You could imagine that it's hydrogen bonding to some group on the substrate as well as interacting with functional groups on the side chains of the enzyme. And this looks somewhat similar to the previous mixed non-competitive or non-competitive mode, but because it doesn't bind to the free enzyme, it actually simplifies dramatically the effect on the dependence of the velocity on the concentration of substrate. What we find is that Vmax, of course, will decrease. We can reason, because this binds to the Michaelis complex, no matter how much substrate we have, we can saturate, imagine trying to saturate our enzyme with substrate by making the substrate concentration very large. The inhibitor will still bind and take some of that complex out of commission and put it into this inactive form, reducing the Vmax. So we can expect the Vmax to shift. But in this case, we also expect the Km to decrease. Now that's unusual. What it implies is that the binding of the substrate will actually, in some sense, the effective equilibrium constant will shift, and you will see more complex than you would expect. You would see less free enzyme, less free substrate than you would expect. One way to think of it is that since the inhibitor binds to this, that binding state must, in some sense, lower the energy or stabilize the ES complex. So it binds and stabilizes it and holds it in the stable form. And that has the effect of decreasing the Km. Now what I won't derive here, it turns out that the Km decreases by exactly the same factor as the Vmax. Okay, so Km and Vmax both decrease, and importantly, by same factor. That has important implications for the plot. Let's show that graphically. Here is our Lineweaver-Burke plot. Inverse substrate, inverse reaction velocity. There's our negative inverse substrate axis. Let me draw a uninhibited reaction velocity or inverse velocity graph. As the Km decreases, that implies something unusual, that the intercept, because the intercept is the negative of the inverse, the magnitude of the intercept will increase because Km gets smaller, so that means it will shift out here to the left. But the slope, now the slope, remember the slope is Km over Vmax, right? So since they both decrease by the same factor, the slope remains constant. This is very characteristic change. So you get a shifting of the intercept, but the slope stays constant. This is increasing inhibitor concentration.